Hi friends, so it's quite some time that I wanted to create some video series about vector sets. Not because the documentation is not good enough, because it's, I believe, quite complete, but perhaps in the video format it is possible to also say things that you normally don't say much in the documentation, especially the fact that vector sets are so different than other vector database solutions. And the fundamental difference is that while vector sets think at vectors and vector data structures used to take the similar vectors to a given query as a data structure, other databases think at vectors as an index or as a complete solution about vectors. So as a database product itself, or at least as an index type of some kind of database that is already able to index stuff. Instead, in Redis, everything is a data structure, so also vectors and especially HNSWs in this case, which is the graph data structure that are able to reply very fast and in a convenient way to the query, I have this vector, give me all the similar vectors, is a data structure per se. And let's start showing you what this means in very practical terms. So let's spin a Redis instance here. Okay. This is Redis unstable, but you can find the implementation of vector sets also in Redis 8 and greater. However, please download the most recent version as possible, because there are improvements made lately if you want to experiment with it. Let's run the CLI. Actually, before that, I wanted to check another thing. Because this is the first data structure introduced after so many years. So for example, if I do git log t stream.c, and I believe this is the last data structure introduced, it is 2017, so it's a lot of years past. And then so even when I was still in Redis for 3 years, I didn't add any data structure and was very focused on consolidating certain things, especially I was doing in the latest years before leaving and then rejoining a few months ago. I was doing a lot of work on client-side caching and stuff like that. So really a lot of time. And after streams, vector sets are the first new data structure. By the way, it's interesting that sometimes new data structures take a lot of time in order to be accepted by the community. This happened also with Lua scripting, which is now one of the most important features of Redis, used over the years in order to do everything. But initially there was a very big inertia to adopt them. And now my colleagues that have the statistics about the Redis usage in the Redis cloud, they say me that streams are really getting more and more traction and are used a lot in many use cases. So after so many years, we have a new data structure. As every data structure in Redis, there is one letter which is the prefix of all the commands that have something to do with this data structure. So what are vectors? Vectors are just floating point numbers, an array of floating point numbers. And vectors become interesting when you add them to a data structure that is able to retrieve very fast elements which are similar, near to other elements. The distance function, however, must be chosen in a peculiar way based on what you want to do. For example, Redis does not support Euclidean distance. So for example, you cannot model right now, but maybe I will add this later. Give me the points in the 3D space which are near the others. It will be absolutely able to do that. What is missing is a little glue, but this is all the implementation is designed to be extremely fast, efficient for the specific use case of statistical properties between vectors. And in this case, what you want to do is to use the cosine similarity distance. The difference is that if you imagine these vectors, these numbers, as point in an n-dimensional space, so if you have vectors of 3 components, they are 3D points. If you have vectors of 10 components, you have a space of 10 dimensions, and they are points in this multidimensional space, and so forth. In this case, and instead of checking how far is one point from the other, we check if vectors, so imagine they start at the origin, for example, if they point towards the same direction. And this is a lot more meaningful when you want to check vectors that are about features that a given object has. So I want to make an example about this. For example, imagine to have the cardinal points north, northeast, east, and so forth. And you can imagine this in the center here to be 0, 0, so the origin. And then this is, for example, if we imagine this to be a x and y, this is, for example, 0, 1, this is 1, 1, and so forth. This is 1, 0. And this is a good way in order to show you vectors. For example, in order to add a vector, this the database is completely empty. You use the VADD command, my key, values. For example, I have 3 components in my vector, so I write 3, 1, 2, 3, and then I give my item a name, foo. Then I can add another 1, 1, 1, 1, bar. Okay. So this is very similar to sorted sets in Redis, but instead of the elements of being associated with a score, they are associated with a vector. So what is the cardinality of my key is 2. There are 2 elements. What is the dimension of my key? It's 3 components. With VINFO I can get a bunch of information about the underlying data structure used here. For example, the quantization type that we will see later, because vectors being floating point numbers occupy a lot of memory, and by default Redis use quantization representing each vector as an integer of 8-bit. And then what's the M parameter of the HNSW, which is 16 by default, the dimension if there is any projection in order to reduce the dimensionality of the vectors. There are many advanced features that we will explore in the next videos. So in order to add my cardinal points here, I wrote a script, otherwise it's super boring to watch, where we just add our coordinates for north, northeast, east, south, southeast. So it's always the same format. VADD, the name of the keys, values, and you can also add, if you want, you can write, if instead of values you can have something like that, FP32, and then a blob string representing your basically binary array of floating point numbers, and it's much faster to parse by Redis and also to generate by your client. But this is a, you know, there must be always a form which is playful and nice to work with. And then if you want to optimize things, there are the ways to make things more obscure and more fast. But I prefer to just act with the data structure just using values. So let's run this script. Okay. And we added all this stuff. So the first return value is the one from delete, okay, and then the VADD all return true because the element was just created. Okay, now if I check the cardinality of test, it contains 8 points. And I can explore finally the most important command of vector sets, which is VSIM, where I tell give me similar points to. So VSIM test. Similar to what? I can specify either an element which is already inside the set, and I tell the implementation give me similar elements. And what are the elements similar to north? North, then there is northeast and northwest, then east and west, then southeast and southwest, and then south, which is the opposite vector. And if I ask with scores, I can see a similarity score, which is 1 if the vectors are towards the same exact direction, and 0 when they are facing completely in the opposite direction, and 0.5 when they are orthogonal, basically. So this very simple example shows us this very specific thing. And of course you cannot have just 0 or 1. For example, we can ask also what is a vector of a given element, and for north is 0, 1, for east is this one, actually in English is east, sorry, this is Italian, and so forth. But of course you cannot just have 0 or 1, you can have 0.001, 2.345, and upon insertion Redis will normalize these values, because normalized values are much faster in order to perform the similarity, the cosine similarity, because for a very simple mathematical equivalence, cosine similarity is the same as dot product if the vectors are already normalized, and dot product is very fast to compute. Another example that I wanted to do, and I tried to prepare some scripts here, is that imagine that you have bitmaps, okay, bitmaps like this, where you have points that are on and points that are off. The dots are points set to 0. And you want to retrieve similar images to this bitmap. So you have a collection of bitmap. So I created a script that adds a lot of random vectors with 0 and 1 based on this 8 by 8 grid of points, so each vector is 64 components. And then I have a search script which will read a pattern from a file name and will search for similar items to it. Please note that the space of 8 by 8 is very big. Sorry, it's very big, so it's very unlikely that we will find the perfect shape. Also because the points here are totally random. Each point has 50% of probabilities to be on or off. But still, if I run the script that adds, I also need another shell, another tab here, because I will also search at the same time for my pattern. Exactly, Python 3. My pattern is, okay, query pattern. It's displayed here, no similar pattern found, because still I have to launch my script and I want to add 1 million elements. So when I start to query it, I find just things that are very far. Well, there is something that more or less approximates a bit more, but the minimum distance is 0.719. If I ask it again, now, okay, we improved, because now I have this kind of similarity. The best similarity before was this one, and yeah, it's a bit more similar. As you can see here, it's a bit more similar here, and the more I will let it run, and the more I will be able to find kind of similar images. Let's check the other pattern. Okay, this is more clear. So this is the query pattern, and here are the patterns that I get returned. So just to say, if I stop this here and I don't add any more patterns, out of all the images inside, which are a lot are totally random images, mostly are totally random, just noise points, it is immediately so fast able to retrieve similar patterns. And also if I get this pattern here, this image here, VSIM test what I did wrong, okay, it's not test, sorry, the key is images. VSIM test okay, as you can see, we get the images and the distance, and I can use here count to get a lot of items, and as you can see, they start the numbers start to increase as there are more differences in the pixel set and not set. And you here don't see smooth changes because there are a lot of images that have the same amount of misplaced pixels. Okay, so the distance will be the same. But what's interesting is that in this specific case, I can use, okay, vinfo here images will tell us that we have already 150 key images inside our index, and if I do Redis benchmark of this command line here, you will see that it is a very fast implementation, because vector similarity is slow. You have to optimize your stuff very well, but Redis is able to provide very high numbers of requests per second, and this is not single core as Redis usually does. I wrote this implementation with threading in mind, because in this specific case threading is absolutely needed. There is also no thread. Exactly. Look at this. This is single core, 18K, and this is multi-core, and is like 5 times more or something like that. So it's really important. Another thing, I want to save this dataset to show you that the implementation is also extremely fast. If you are not into vectors, you may not appreciate this a lot, but you need to know that vectors are extremely hard to insert very fast in the HNSW data structure, which is HNSW is this multi-layer data structure, which is quite complicated, and I implemented a new implementation from scratch from the paper for Redis, and so the Redis implementation it does one thing. Instead of just storing the item name and the vector and then inserting back the vectors inside the HNSW data structure, I serialize the graph on disk, so loading back is very fast. For example, if I start Redis, it took just 0.784 seconds in order to reload this back. Okay, so I want to show you, so far we saw how this works without AI things, and also without AI you can do a lot of cool things. For example, some time ago I published this this blog post where you can basically find duplicated fake hacker news accounts, you know, the kind of accounts that people create in order to say what should not be said with your name attached to it, and basically you can find for similar, for example, what are the similar users to Paul Graham, and those are what are the similar users to Antireds, and this is more than 500,000 Hacker News users. This is $5 per month or something like that instance running, very old instance running in some cloud provider, and well, you can model quite interesting things, and this is done without AI, just basically computing fingerprints that you can see here graphically of the way the users use the most common words. What is the frequency they use a given word more than often, and what is the set of words they use less than often compared to the site corpus average. So you can do a lot of interesting things with vector sets without AI. But of course, the most important application of vector similarity is in searching for similar things using learned embeddings. So learned embeddings, what are basically, there are AI models where you can put an object and they transform this object in the vector that basically is the meaning of the object. So if you want to capture similar sentences, you pass your sentences into an embedded model, in an embedding model, then you add your vectors inside Redis, and then what you can do is basically use of the VSIM command in order to get similar items. But the very cool thing is that you also have multimodal embedding models, so you can also turn an image into a vector and also a text into a vector, and the vectors will be in the same space. So you can search like Google Photos, for example, for images matching a given sentence. So if I search the image of myself with a red cap on the beach, I will find such images because both my query and the images that I have in my Google Photos passed inside an embedding model. So I want to show you this use case as well. And for example, here I have, okay, let's start with words. This is a data set of the very famous Google Word 2 vec, where each word was translated into a vector. This is a very basic embedding model that was used for many years in the industry and in search and so forth. So it's a good starting point, and then I will show you some more modern embedding model. It will take some time in order to load because the vectors are large and there are 3 million words. So also this is also a good use case in order to see what you can expect in terms of loading time from Redis. For example, this took 30 seconds, but let's see what we have here inside. Word embeddings, vinfo. Okay, quantization is 8-bit, but this also has attributes, and so it was slower to load. Otherwise 14 seconds are enough for 3 million elements, and I will show you what attributes are later in a few minutes. So let's start with this is my key, vrand member. I find random sampling very nice, in order, you can specify how many random elements you want. It's I believe it's very nice in order to play with that data set and understand what's inside. There are all the kind of scientific terms, words, and brands, whatever. But I want the similar words to ice cream, and the similar words are ice cream, ice creams, and so forth, lollies, biscuit, Mr. Whippy, I don't know what it is, maybe it's an ice cream brand in the United States, I have no idea. Let's try with banana, bananas, pineapple, mango, papaya, coconut, potato, cashew, melon, so all fruits. Count. I want also to show you how fast this stuff is. It's really incredible, and you just see foods here. You see, and let's check with BASIC, the programming language. BASIC Fortran computing. So it's incredibly powerful. And you can do really interesting things with it. Also, I want to show you another thing. I already showed how you can ask the index what is the vector for a given element, okay, and it will return a bunch of numbers. Oh, okay, no problem. So I can do this vemb. this is my key name, and this is my element, and it will return my numbers. And I wrote this very similar, this very simple utility, VShow, that turns the embedding into an image, but this is not the good terminal to do this because I need ghosty. I normally use ghosty as oh sorry, I don't have a show here. YouTube sets CLI. Okay, ghosty can display using the Kitty protocol images in your terminal, and I find this to be terrific. So basic is this image, banana is this image, so we'll have different patterns and so forth, but maybe Fortran will have an image similar to, more similar to basic. Unfortunately, I don't have here a tool in order to compare the two embeddings, but stay sure that there are similarities among similar embeddings. And this time I want to load a different dataset which is called food. Let's copy this here, and it will take like 10 seconds in order to load. And this this dataset was created in a different way. Basically, let's close this. Okay, food items. Rand member food items. There are just foods with their calories, proteins, all the nutritional facts basically. And these embeddings were, so each of course food items, each of these items is associated with a given vector, right? As usually. Exactly, and these vectors are very large and very meaningful. And I created this with a very valid open source embedding model, mxbay large embedding. This one created by Mixed Bread AI, and it's super cool, works very well. And I use Ollama in order to create these embeddings. So to turn a sentence into an embedding is a very similar process. Okay, look at this. It's just a get HTTP request. So I have Ollama running on my system, so localhost, embeddings, and what I want to pass is the model name, mxbay embed large, and the prompt is the sentence that I want to turn into a... Let's run this. Probably my computer needs to load the embedding model in order to reply. So it will take some time. Exactly. So what are vectors? Just a bunch of numbers that have meanings. And so now I would love, for example, to ask, I have my key and this is full of items. Vinfo, let's see how many items. Yeah, there are more than 1 million foods inside, so it's really interesting. And what I want to do at this point is to ask to write a sentence, and I want similar foods. However, to do that I will need to perform the query like VSIM food items, and then values, and I have to copy in some way these numbers here, which is extremely uncool. So I created this very small script, which is basically a Redis CLI, but has this special form so that I can write VSIM food items. And here I can write something like chocolate ice cream, and I get immediate, this Python program asks Ollama to turn this sentence into a vector and then unpacks values with all the 1024 components for me. I wanted to implement this in Redis CLI, but this would require to have SSL as a requirement in order just to compile Redis, and it's not great. We will find a solution. So let's look at this chocolate ice cream and so forth. Let's elements similar to Italy, Italian something, elements similar to tagliatelle. It's a kind of pasta. Tagliatelle everywhere. Sweet fruit. Fruit of many kinds. Or se no, otherwise programming. Food similar to programming language. I can't believe this. Java probably is a coffee or something like that. Computer science with Python. This database is a bit contaminated by non-foods. Okay, at this point I want to see if there are food items similar to antireds. No, but it kinda captures also the sound of the sentence. It's super interesting. Okay, so far you can say this is cool and all, but I want to not just similar items, but I want to filter by other things, and you can, because maybe in this specific data set I didn't add the attributes. No, but we can very easily load back the other data set, the words.rdb, dump rdb, and we restart Redis, and unfortunately there is to wait a bit, maybe a bit less this time because it's inside the cache. Okay, 29 seconds. So we are back here to our banana example, but each element in a vector set can also have a JSON attribute, which is free form, but it must be flat, just one level, non-nested elements. So we get attr, this is my key, banana, len6. Basically this JSON attribute that I used here, it's just the length of the string, but you can put inside whatever you want. So the super nice thing of the VSIM command is that it has a filter option where you can specify like expressions, like if you are inside an if statement of a programming language, and you can reference the JSON attribute of the object with dot. So .len equal 10. So I want elements that are similar to banana, but only if they are exactly then bytes, like then characters. So pineapple, strawberry, sugarcane, and 20. Of course, there are less similar items in this group, and you can see that it remains extremely fast. And in the next episodes I will show you how this was implemented, because in order to do that I extended the paper. Actually the HNSW Redis implementation contains many extensions of the paper. For example, if I want to remove an element here, v del word embeddings apple, sorry, vrem, this is true deletion, sorry, not thumbstone deletion. So we freed the memory used here, which is not easy. And there are also other extensions that I did to the algorithm in order, for example, to make sure that after elements are removed, the neighbors are, you can, this implementation also allows you to look inside the HNSW. So what are the edges connected to, of banana connected to? What are the links, the similar items in the graph? So it's connected, banana has a single level, it could have multiple levels. We just got one element with a similar single level, and you can see the edges it is connected to. But I will dive into the implementation itself in the next videos. Right now, you know that we also have the ability with Redis vector sets to not just have similar items, but to filter by other stuff. And when the problems at hand are complicated enough, this is extremely needed. Okay, so see you in the next episodes, and bye. Thank you for watching.